Hey there, beautiful human. It's your boy Chad, your relaxing galactic guide with a level of cosmic understanding that, honestly, should be studied by scientists. Where are you watching from tonight? Tucked into bed with your phone propped on a pillow? Sprawled on a couch with a cat on your chest? Maybe you drove out somewhere dark and quiet and you're watching this from a car windows down with actual stars overhead. Because if that's you, you are truly winning at life. Wherever you are, get comfortable, because tonight we are delving into the strangest, most mind-rearranging world ever discovered, the quantum realm. So nestle in, because things are about to get weird. Let's begin. Quantum mechanics. Even the phrase sounds like it belongs in a science fiction film, like something a character with a holographic clipboard says before the plot gets complicated. But quantum mechanics is not fiction. It is, in a very real sense, the most accurate description of physical reality that human beings have ever produced. It is the rulebook for the universe at its smallest scales, the laws governing atoms, electrons, photons, and the invisible architecture of everything. Everything you have ever touched, seen, tasted, or thought about is made of things that obey the laws of quantum mechanics. The coffee cup on the nightstand, the air moving through your lungs right now, the neurons firing in your brain as you process these words. All of it, at its deepest level, is quantum mechanical. So what exactly is quantum mechanics? Let us start with the word quantum. It comes from the Latin for how much, and in physics, a quantum is the smallest discrete unit of something, the tiniest indivisible packet. Think about this carefully for a moment. Imagine you are pouring water from a pitcher. The water flows in a smooth, continuous stream. You can pour any amount, a lot, a little, an infinitesimally small drizzle. There is no minimum unit of water you are required to pour. Water, in this sense, is continuous. Now imagine instead that you are handing out coins. You can give someone 1 coin, or 5 coins, or 100 coins, but you cannot give them half a coin, or a third of a coin. The coin is the minimum unit. Everything must come in whole numbers of coins. That is what physicists mean when they say something is quantized. It comes in fixed, irreducible amounts, not in a continuous flow. Quantum mechanics tells us that energy, at the level of atoms and light, behaves like coins rather than water. It does not flow in continuous streams. It comes in packets, quanta, and this seemingly modest observation cracked classical physics open like an egg and changed everything inside. Now, why should you care about this beyond mere intellectual curiosity? Here is why. Quantum mechanics is not abstract background scenery. It is the foundation upon which the entire technological world is built. Lasers exist because of quantum mechanics. Transistors, the tiny switches that make computers possible, are quantum devices. The MRI machine that can peer inside your body without cutting it open operates on quantum principles. Solar panels, LED lights, semiconductor chips, fiber optic communications, electron microscopes, and the nuclear reactors that power cities. All of them are applications of quantum mechanical understanding. When scientists learned how quantum mechanics worked, they did not just gain knowledge, they gained a toolkit that remade civilization. But the technology is almost a side note to what makes quantum mechanics truly extraordinary, because beyond the practical applications, quantum mechanics is philosophically staggering. It forces us gently but insistently to revise almost every intuition we have about how the world works. Does a particle have a definite location before we look for it? Quantum mechanics says, not necessarily. Can two particles, separated by an arbitrarily large distance, remain instantaneously connected in a way that no classical concept can explain? Quantum mechanics says, yes. Is the fundamental behavior of nature deterministic, or is genuine randomness built into the very structure of reality? Quantum mechanics, in the interpretation most physicists work with, says the latter. These are not small questions. They are the deepest questions we can ask about the nature of reality, and quantum mechanics does not shy away from them. It bulldozes through them with mathematical precision and experimental certainty, leaving us standing in the rubble of our old assumptions, slightly dazed and genuinely astonished. The story of how quantum mechanics came to be is one of the great intellectual dramas in history. It took place across roughly 3 decades, from the closing years of the 19th century to the late 19th. It involved some of the sharpest minds who ever lived, many of them very young, working in a state of near-frantic excitement, and in many cases, profound personal discomfort with their own conclusions. Over the next hour, we are going to move through this story with care. We will begin with the crisis that first broke classical physics open. Then we will explore wave-particle duality and the double-slit experiment. We will sit with the uncertainty principle and understand what it truly says. We will spend time with superposition, the idea that quantum systems exist in combinations of multiple states simultaneously. We will encounter entanglement, perhaps the most haunting and philosophically loaded phenomenon in all of science. We will look at quantum tunneling and the remarkable things it makes possible, and we will close by stepping back and considering what all of it means for science, for philosophy, and for how we understand the universe we find ourselves in. Take your time with each idea. Let the strangeness settle. Some of these concepts will feel slippery and elusive at first. That is not a sign of confusion. That is the correct response to quantum mechanics. Richard Feynman, one of the most brilliant physicists of the 20th century, once said that if you think you understand quantum mechanics, you do not understand quantum mechanics. We are in good company in our bewilderment. The story of quantum mechanics does not begin with an atom or a particle. It begins with light and heat. Specifically, it begins with a puzzle that physicists in the late 19th century called black body radiation, and with a crisis that exposed a fatal flaw lurking inside what had seemed like a triumphant, nearly complete picture of the physical world. To appreciate that crisis, you have to understand how confident physicists were in the 1890s. Classical physics, built on the foundations laid by Isaac Newton 2 centuries earlier, refined and extended by countless contributors, had achieved extraordinary things. It could predict the motion of planets with stunning precision. It explained how heat flowed, how engines worked, how gases behaved under pressure. James Clerk Maxwell had unified electricity, magnetism, and light into a single elegant theory of electromagnetic waves. Everything seemed to fit together beautifully, like a vast and intricate clockwork. There is a sentiment, often attributed, perhaps a little unfairly, to the physicist Lord Kelvin, that physics was essentially finished, that the laws of the universe had been found, and what remained was merely the filling in of decimal places. The universe, on this view, was a machine. Its rules were known. Time was running out for big discoveries. And then a handful of experiments produced results that absolutely refused to fit the classical framework, and the clockwork universe began to come apart. The black body problem concerned the way heated objects emit light. A black body, in the physicist's idealized sense, is an object that absorbs all radiation that falls on it and re-emits that energy, purely based on its temperature. When you heat a piece of iron in a forge, it begins to glow, first a deep red, then orange, then yellow, then white as it gets hotter and hotter. The color of that glow is determined entirely by the temperature. This is black body behavior, and it was a well-studied phenomenon. The trouble was that classical physics, when applied to predict exactly how much radiation a black body should emit at each frequency, produced a catastrophic result. The equations predicted that a warm object should radiate an infinite amount of energy at high frequencies, infinite energy pouring from a warm kettle, infinite energy from a glowing piece of iron. This was obviously absurdly wrong. Physicists called it the ultraviolet catastrophe, because the divergence happened toward the ultraviolet end of the spectrum. The existing framework of physics could not fix it. The equations were internally consistent, but they led to nonsense. In the year 1900, a German physicist named Max Planck decided to work backward from the experimental data. He knew what the correct radiation curve looked like. Experiments had measured it carefully. He set out to find a mathematical formula that would reproduce those measurements, and he found one. But to make it work, he had to introduce an assumption that troubled him deeply. He had to suppose that energy was not emitted continuously, but only in discrete packets, quanta, whose energy was proportional to the frequency of the radiation. He introduced a tiny constant of proportionality, now called Planck's constant, and denoted by the letter h, to set the scale of these packets. The formula worked with breathtaking precision. It matched the experimental data perfectly across all frequencies. But Planck himself did not entirely trust what he had done. He suspected he had introduced a clever mathematical trick, a useful fiction to make the equations behave, rather than a genuine physical truth. He spent years afterward trying to find a way to derive his formula without the quantization assumption. He never succeeded, and in his Nobel Prize lecture in 1918, he admitted as much with characteristic honesty. 5 years after Planck's formula appeared, a young man named Albert Einstein picked up the quantization idea and took it somewhere far more radical. Einstein, who in 1905 was 26 years old and working as a technical examiner in the Swiss Patent Office in Bern, having failed to secure an academic position, published 4 papers in that single year, any one of which would have been enough to make him famous. One of them explained Brownian motion, the jittery random movement of small particles in a fluid. One of them introduced special relativity, one derived the famous equation E equals mc squared, and the fourth, the one for which he was actually awarded the Nobel Prize in 1921, explained the photoelectric effect. The photoelectric effect was another of those stubbornly anomalous experimental results. When ultraviolet light shines on a metal surface, it can knock electrons out of the metal. This much was known. What was strange was the pattern of when and how electrons were ejected. Classical physics predicted that brighter light, more intense light, should knock out electrons with more energy, but experiments showed that the energy of the ejected electrons depended not on the brightness of the light, but on its frequency, its color. Dim violet light could eject highly energetic electrons. Bright red light, no matter how intense, could not eject electrons at all. Einstein's explanation was breathtakingly simple and deeply radical. He proposed that light did not travel as a continuous wave, but was made up of discrete packets of energy, what we now call photons. Each photon's energy was determined by its frequency, following exactly Planck's formula. Energy equals Planck's constant times the frequency. A single photon of violet light carried more energy than a single photon of red light. Only a photon with enough energy could knock an electron free. No matter how many low-energy red photons hit the metal, none of them individually had enough energy to do the job. This was the moment that quantization moved from a mathematical convenience to a physical reality. Light itself, which had been irrefutably shown to be a wave by 2 centuries of careful experiment, was also somehow a particle. And this tension between wave and particle would come to define the entire strange enterprise of quantum mechanics. Light as both a wave and a particle. This sounds at first like a contradiction, and in the everyday world of human experience, it would be. A wave is a spread-out, continuous disturbance. A particle is a compact, discrete object. These two things seem mutually exclusive, but quantum mechanics insists they are not, and the most vivid demonstration of this insistence is an experiment so elegant and so disturbing that physicists have been thinking about it for nearly a century. It is called the double-slit experiment, and it contains, as Richard Feynman once said, the entire mystery of quantum mechanics. Imagine a flat barrier with 2 narrow vertical openings in it, 2 parallel slits. On one side of the barrier, you have a source that fires particles. Let us begin with photons, particles of light. On the other side of the barrier is a screen that records where each particle lands, building up a picture over time as particle after particle arrives. Now, if photons were simple classical particles, like tiny marbles, you would expect a simple result. Some photons go through the left slit, some through the right, and they hit the screen and pile up in 2 corresponding bands, one behind each slit. Clean, predictable, boring. What actually appears on the screen is something else entirely. Instead of 2 bands, you get a pattern of alternating bright and dark stripes spread across the entire screen. This is an interference pattern, the unmistakable signature of waves. When waves pass through 2 slits, they spread out on the other side and overlap. Where the peaks of 2 waves meet, they reinforce each other. Bright stripes. Where a peak meets a trough, they cancel out dark stripes. The screen fills with a beautiful, regular alternating pattern of light and shadow. So photons are waves. Fine. But wait, photons are also particles. They arrive at the screen as individual, localized impacts, one at a time. Each one lands at a single point, and yet over thousands and thousands of individual impacts, those points accumulate into the interference pattern. The pattern emerges from countless individual particle events, each seemingly discrete, building up collectively into something that only waves can produce. The obvious question, maybe the photons are somehow interacting with each other as they pass through the slits. Maybe the waves are produced by the collective behavior of many photons. Let us test that. Let us turn the source so dim that only one photon is emitted at a time, so that each photon travels through the apparatus completely alone, with no other photon anywhere near it. Still, over time, the interference pattern builds up. Each individual photon, traveling alone, somehow passes through both slits simultaneously, interferes with itself, and arrives at the screen at a location determined by that self-interference. The single photon by itself produces the pattern. Now here is the part that truly breaks your brain. What if we put detectors at the slits, to record which slit each photon goes through? Surely we can settle the question of whether the photon really goes through both. Let us just watch. When detectors are placed at the slits, when we measure which path each photon takes, the interference pattern vanishes. The screen shows two bands. The photons behave like classical particles, going through one slit or the other, landing in a pattern that reflects that. The act of measuring which path was taken destroys the interference. The moment we gain information about which slit the photon used, it stops behaving like a wave spreading through both. This is not a failure of technology. It is not that the detectors are clumsy and disturb the photons by accident. It is that the quantum state of the photon, its wave function as we will come to call it, is fundamentally altered by the act of acquiring information about it. When its path is measured, the photon no longer exists in a superposition of went through left slit and went through right slit. It is forced by the measurement into one definite state, and a particle that went through only one slit produces no interference. This same experiment can be performed with electrons, with atoms, and even with molecules as large as a few hundred atoms. In every case, the results are the same: wave behavior when unobserved, particle behavior when measured. The quantum world does not commit to definite behavior until it is probed. The mathematical framework that describes this behavior was developed in the 1920s by a generation of young physicists working in a state of almost feverish intensity. Erwin Schrödinger, an Austrian physicist with a gift for elegant mathematics, formulated the equation that governs how the quantum state of a system evolves over time. This quantum state is described by what we call the wave function, a mathematical object that encodes all the probabilities associated with possible measurement outcomes. The wave function of a particle spreads through space like a wave, with its intensity at any location telling you how likely you are to find the particle there if you look. But the wave function is not like a classical wave in water or sound. It is a probability wave. It does not represent a physical disturbance spreading through a medium. It represents the quantum state of possibilities. Before measurement, a particle does not have a definite position. After measurement, it does, and the wave function is said to collapse from a spread of possibilities to a single definite outcome. Werner Heisenberg, a German physicist working at the same time as Schrödinger, developed an alternative mathematical formulation of quantum mechanics, one using matrices rather than differential equations, that turned out to be mathematically equivalent to Schrödinger's approach. The two formulations looked utterly different on the surface, but described the same physics. Paul Dirac, a precise and almost eerily brilliant Englishman, later unified them into a single, more general framework that became the standard language of quantum mechanics. These three men, and a handful of collaborators including Niels Bohr, Max Born and Wolfgang Pauli, built the core of quantum mechanics in the span of just a few years. They were all young. Heisenberg was 23 when he made some of his most important contributions. The speed and intensity of the work was extraordinary, driven partly by the feeling that they were not just solving problems but rewriting reality. Out of this theoretical work emerged one of the most celebrated and most frequently misunderstood statements in all of science: Heisenberg's uncertainty principle. You have likely heard of it, but let us be careful here, because the casual version, "you can't know everything about a particle," understates it in a way that misses the real point. The uncertainty principle is not primarily a statement about the limits of measurement. It is a statement about the fundamental structure of nature. Here is what Heisenberg discovered in 1927. Certain pairs of physical properties, called conjugate variables, are linked in such a way that the more precisely you know one of them, the less precisely it is possible, even in principle, to know the other. The most famous pair is position and momentum. Momentum is, roughly, mass times velocity. It tells you how fast something is moving and in what direction. The more precisely you know where a particle is, the less precisely you can know its momentum. The more precisely you know its momentum, the less precisely you can know its position. And this is not a problem with instruments. It is not something that better technology could resolve. Even with perfect instruments, in an ideal world, this limitation would remain. It is written into the mathematics of quantum mechanics at the most fundamental level. To understand why, consider what it means to describe a particle with a well-defined position. Such a particle would be represented by a wave function that is sharply peaked at one location, a narrow spike. But in mathematics, a sharply localized spike is built from a superposition of an enormous range of frequencies. And in quantum mechanics, frequency corresponds to momentum, so a well-defined position requires a huge spread of possible momenta. Conversely, a particle with well-defined momentum is described by a wave function with a precise single frequency, but a wave with a single frequency extends uniformly through all of space. It has no localized peak at all. Such a particle could be anywhere. Its position is entirely uncertain. Think about trying to photograph a hummingbird in flight. With a very fast shutter speed, you freeze the bird's position perfectly. You can see exactly where it is, sharp and clear, but the frozen image gives you no information about how it was moving or in what direction. The motion is invisible, captured at a single instant. Now switch to a slow shutter speed. The bird blurs across the frame as it moves, and now the image tells you something about its trajectory and speed. But you have lost the precise position. The bird is smeared across the photograph. You are trading off one kind of information for the other. No shutter speed gives you both perfectly. Quantum particles face an analogous trade-off, except that it is not about camera settings. It is about the wave mathematics that describe them. Position and momentum are not two separate properties that happen to be hard to measure simultaneously. They are mathematically intertwined such that precision in one necessarily entails uncertainty in the other. The uncertainty principle has a consequence that is easy to overlook but astonishing when you absorb it. Nothing in the quantum world can be perfectly at rest. If a particle had zero velocity and a fixed position, both its momentum and its position would be perfectly known, which would violate the uncertainty principle. So even at absolute zero, the coldest possible temperature, where classical physics predicts all thermal motion ceases, quantum particles retain an irreducible residual motion called zero-point energy. The quantum world cannot be fully still. This is not theoretical speculation. Zero-point energy has real measurable consequences. Liquid helium, even at atmospheric pressure and temperatures approaching absolute zero, refuses to solidify. The zero-point motion of its atoms is just enough to prevent them from locking into a solid structure. No other element behaves this way. It is a direct macroscopic consequence of quantum indeterminacy. Heisenberg was 25 years old when he worked out the uncertainty principle. He was staying at a research institute in Copenhagen, and he has described the moment the mathematics clicked into place in the small hours of the morning, after days of intense concentration. He was so unsettled and so excited by what he had found that he went outside for a walk in a park near the institute and stayed there until dawn. The uncertainty principle is part of a broader pattern of irreducible randomness and indeterminacy in quantum mechanics. This randomness was perhaps the aspect of quantum mechanics that disturbed classical-minded physicists the most. Newton's universe was deterministic. If you knew the position and velocity of every particle at one moment, you could in principle predict the entire future of the universe. Quantum mechanics destroyed this picture. Knowing everything that can possibly be known about a quantum system, you still cannot predict with certainty what will happen when you measure it. You can only calculate probabilities. The randomness is not due to ignorance, it is fundamental. From the wave function and the uncertainty principle, we move naturally to one of the deepest and most philosophically loaded ideas in all of quantum mechanics, the idea of superposition. We have already encountered it in the double-slit experiment, but let us develop it more carefully, because it is the key to understanding everything that follows, including entanglement and quantum computing and Schrödinger's famous cat. In classical physics, a system is always in one definite state. A coin is heads or tails, a switch is on or off, a particle is here or there. The state of the system is a fixed fact, independent of whether anyone is looking at it or measuring it. Quantum mechanics says this is simply not how nature works at the fundamental level. A quantum system is described by its wave function, which can be a superposition, a combination of multiple possible states at once. And this superposition is not a statement of ignorance. It is not saying the particle is in one definite state, but we don't know which one. It is saying that prior to measurement, the particle genuinely exists across all those states simultaneously, with each state weighted by a certain probability amplitude. The clearest example involves a property called spin. Electrons possess an intrinsic property called spin, which has no exact classical analogue. It is a kind of built-in angular momentum. When you measure an electron's spin along any axis, you always get one of exactly two results: spin up or spin down. It is a binary property, like a coin that can only be heads or tails. But before you measure it, the electron's spin is not secretly heads or secretly tails. It is in a superposition of both states. The spin is genuinely indeterminate until the moment of measurement. Measuring it does not reveal a fact that was already there. It participates in creating that fact. The outcome is random, with probabilities determined by the wave function. This was deeply troubling to Einstein and to many classically trained physicists. It seemed to suggest that reality was incomplete or unformed until observed. Einstein famously asked his colleague Abraham Pais whether he truly believed the moon was not there when nobody was looking at it. It was not a flippant question. It expressed a real philosophical resistance to the idea that the physical world required observers to be definite. The interpretation of what superposition means, what is actually happening in the physical world when a quantum system is in a superposition, remains one of the most debated questions in the foundations of physics. One view associated with the Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg is essentially agnostic. It holds that quantum mechanics is a tool for predicting measurement outcomes, and that asking about the true state of the world prior to measurement is not a meaningful scientific question. The wave function is a calculational device, not a direct picture of physical reality. Another view, proposed by the American physicist Hugh Everett III in his 1957 doctoral dissertation, takes the wave function at face value. In Everett's picture, now called the many worlds interpretation, the wave function never collapses. Instead, every quantum measurement causes the universe to branch into multiple diverging realities, one for each possible outcome. In one branch, the electron was spin up. In another, it was spin down. Both outcomes happen. Both branches are equally real. We are simply unaware of the others. This interpretation sounds extravagant. It requires an almost unimaginably vast number of branching universes, proliferating with every quantum event throughout the cosmos at every moment. Many physicists find it too ontologically expensive to take seriously. Others argue that it is actually the most parsimonious interpretation, because it requires no additional mechanism, no collapse, no special role for observers, just the pure, unmodified mathematics of quantum mechanics taken seriously. The debate has not been resolved. It may never be, but it is worth sitting with, because the question it is asking, what is real and when is it real, is not merely philosophical decoration. It is the heart of what quantum mechanics forces us to confront. Superposition, beyond its philosophical implications, has enormously practical consequences. Quantum computing is built on it. A classical computer processes information using bits, each of which is either a 0 or a 1 at any given moment. A quantum computer uses quantum bits, qubits, which can exist in superpositions of 0 and 1 simultaneously. When you perform a computation on a qubit in superposition, you are effectively performing that computation on both possibilities at once. String many qubits together in a properly entangled state, and you can explore an astronomically large number of computational possibilities in parallel. For certain categories of problems, simulating the behavior of molecules, optimizing complex logistics, breaking or building cryptographic systems, quantum computers hold the promise of capabilities that no classical machine could match. And then there is Schrödinger's cat, a thought experiment proposed by Erwin Schrödinger himself in 1935, not as an endorsement of quantum mechanics, but as an argument against it, or at least against a naive interpretation of it. Imagine a sealed box. Inside the box is a live cat, a small amount of a radioactive substance, a detector sensitive enough to register the decay of a single radioactive atom, and a mechanism connected to the detector that, if triggered, breaks a vial of poison and kills the cat. If no decay is detected, the vial remains intact, and the cat lives. Radioactive decay is a quantum event. The atom either decays or it does not, and before it is measured, it is in a superposition of decayed and not decayed. According to the logic of quantum superposition, the entire system, atom, detector, vial, cat, should be described by a wave function that is a superposition of two states, atom decayed, cat dead, and atom not decayed, cat alive. Before the box is opened, the cat is, in some sense, simultaneously alive and dead. Schrödinger found this ludicrous. He was pointing out that a theory which puts a macroscopic object, a cat, into a quantum superposition cannot be the whole story. Something must happen between the quantum level and the everyday world we experience. Some process must cause the superposition to resolve into one definite classical outcome. What that process is, and precisely where or how the quantum and classical worlds meet, is still not fully understood. It is an area of active research. Some physicists believe that the environment surrounding a quantum system plays the key role, constantly and automatically measuring it through a process called decoherence, which rapidly destroys superpositions in large objects. Others believe something more fundamental is at work. Schrödinger's cat, in a philosophical sense, is still in its box. Now we arrive at what Einstein called spooky action at a distance, what physicists call quantum entanglement. and it is, by any measure, one of the most remarkable phenomena in all of science. Entanglement arises when two quantum particles interact in such a way that their quantum states become inseparably correlated. From that point forward, no matter how far apart the particles travel, they cannot be described independently. The state of one is intrinsically connected to the state of the other. Let us make this concrete with electrons and spin. Suppose we create two electrons in such a way that their total spin must be zero. This means that if one is measured as spin up, the other must be spin down, and vice versa. We then send these electrons off in opposite directions. One travels to a laboratory in Toronto, the other travels to a laboratory in Tokyo. They have never interacted since leaving their common origin. They may be separated by thousands of kilometers. Now the physicist in Toronto measures her electron's spin. She gets spin up. At that instant, not after some signal has traveled across the ocean, but instantly, the electron in Tokyo is determined to be spin down. When the physicist in Tokyo measures his electron, he will get spin down, every single time without fail, regardless of the distance. This correlation is not coincidence. It is not that the electrons decided their spins at the moment of creation, and simply carried that information with them, as if they were two gloves separated from a matched pair, each secretly left or right all along. Careful experiments show that the electrons genuinely did not have definite spins before measurement. The spin of each electron was indeterminate until the measurement happened. Einstein could not accept this. Together with Boris Podolsky and Nathan Rosen, he published a famous paper in 1935, known as the EPR paper, arguing that quantum mechanics must be incomplete. Surely, he contended, there must be some hidden information, some hidden variables that the electrons carry, which quantum mechanics simply fails to describe. The correlations look mysterious only because quantum mechanics is missing part of the picture. With a complete theory, the correlations would be explicable without any spooky action at a distance. This debate was essentially philosophical for nearly 3 decades, because no one could see how to test it. Then, in 1964, an Irish physicist named John Bell, working quietly and almost invisibly at CERN, the European Particle Physics Laboratory, proved something astonishing. Bell showed that if hidden variables existed, if the electrons carried predetermined instructions, then the statistical correlations between measurements on entangled particles would have to satisfy certain mathematical limits, now called Bell inequalities. But if quantum mechanics was correct and the correlations arose from genuine quantum entanglement rather than hidden variables, then those limits would be violated. The debate was no longer philosophical, it was experimental. The experiments were performed, most definitively by French physicist Alain Aspect and his colleagues in the early 1900s. They created pairs of entangled photons and measured the correlations between them under carefully designed conditions intended to prevent any possible classical explanation. The Bell inequalities were violated, precisely as quantum mechanics predicted. Hidden variables could not explain the results. The correlations were real, and they were quantum. Alain Aspect, along with John Clauser, who had performed earlier, less definitive tests, and Anton Zeilinger, who extended the experiments with increasing sophistication over decades, were awarded the Nobel Prize in Physics in 2022. It was a recognition that one of the deepest questions in the history of science had been settled by experiment. Einstein's intuition, compelling as it was wrong. The universe really does have this non-local character. But before you start imagining that entanglement means we can send messages faster than light, and many people have imagined this, let us be clear about why that is not the case. When the physicist in Toronto measures her electron and gets spin up, she gains instant knowledge about the Tokyo electron. But she had no control over which result she got. The outcome was random. The physicist in Tokyo, when he measures his electron, also gets a random result, spin down. Neither of them can engineer their result. They cannot use this to send any message. Only when they compare notes through a normal, slower-than-light communication channel do they discover that their results are always anti-correlated. The correlation is instantaneous. The information is not. The universe is careful in exactly this way. Entanglement is genuinely non-local, but it does not allow faster-than-light signaling. It is as if the universe knows exactly how far it can bend the rules. What entanglement does enable is remarkable in other ways. Quantum cryptography uses entanglement to create communication channels where any eavesdropping is physically detectable. A spy cannot listen to a quantum-encrypted transmission without disturbing the quantum states and leaving evidence. Quantum teleportation uses entanglement as a channel to transfer the complete quantum state of one particle onto another particle, across any distance. Not the teleportation of matter, but the perfect transfer of quantum information. And entanglement is central to the power of quantum computers, where qubits entangled together can represent correlations and explore possibility spaces in ways that classical bits cannot. At a deeper level, entanglement hints at something profound about the structure of reality. Two entangled particles, no matter how far apart, remain in some sense a single quantum system. Separation in space does not dissolve their quantum connection. Some physicists have speculated that entanglement may be related to the very fabric of space-time, that the geometric structure of space itself may emerge from patterns of quantum entanglement at the most fundamental level. This is an idea currently being explored in theoretical physics, and it is far from proven, but it reflects just how deep the implications of entanglement may ultimately run. We have covered the great theoretical pillars of quantum mechanics, but there is one more phenomenon worth exploring in depth, because it is both conceptually beautiful and strikingly practical. It is called quantum tunneling, and it is one of the places where the quantum world most visibly and consequentially reaches into the world we inhabit every day. In classical physics, the behavior of a particle encountering a barrier is completely straightforward. Imagine a ball rolling along a surface and approaching a hill. If the ball has enough kinetic energy to roll up and over the hill, it does so. If it does not, it slows down, stops partway up the hill, and rolls back the way it came. The barrier is definitive. A particle with insufficient energy cannot cross it. Full stop. Quantum mechanics disagrees. Because quantum particles are described by wave functions that spread continuously through space, the wave function of a particle does not simply stop at the edge of a barrier. It reaches into the barrier, and if the barrier is thin enough, it re-emerges on the other side, diminished in amplitude, meaning reduced in probability, but done-go. There is a genuine done-go probability that a particle will be found on the other side of a barrier that it classically had no energy to cross. This is quantum tunneling. The particle, in a sense, tunnels through the barrier rather than over it. Think of it this way. Imagine you are trying to push a ball over a hill, but you do not quite have enough strength. Classically, the ball stops before the summit and rolls back. In the quantum world, you could try the same thing 1,000 times, and on some of those attempts, simply find the ball on the other side of the hill, as if it had slipped through the ground rather than going over the top. The probability depends on how thick and high the barrier is, and on the particle's mass and energy. For electrons, which are very light, tunneling through thin barriers has a significant probability. Now here is why this matters in the most immediate possible way. The Sun is powered by quantum tunneling. In the core of the Sun, the temperature and pressure are high enough to force hydrogen nuclei, protons, very close together. When they get close enough, the strong nuclear force takes over and fuses them together, releasing enormous energy. This fusion is what makes the Sun shine. But there is a problem. Protons are positively charged, and like charges repel. For two protons to get close enough to fuse, they need to overcome this electrostatic repulsion. They need to climb an enormous energy hill. Calculations show that the temperatures at the Sun's core, while extremely high by everyday standards, are actually not quite high enough for protons to classically overcome this barrier. The protons simply do not have enough thermal energy to reach the summit. And yet the Sun fuses hydrogen successfully, and has been doing so for nearly 5 billion years. It can do this because quantum tunneling gives each proton a small but ton-go probability of tunneling through the electrostatic barrier rather than climbing over it. There are so many protons colliding so many times per second that even a tiny tunneling probability adds up to a prodigious rate of fusion. Without quantum tunneling, the Sun would not shine. Without the Sun's light and heat, life on Earth, all of it, would not exist. Every living thing on this planet owes its existence, in a very direct chain of causation, to quantum tunneling. Closer to home, quantum tunneling is essential to the operation of the transistor, the fundamental building block of every electronic device in existence. In modern transistors, which are now manufactured at scales of just a few nanometers, electrons must cross tiny insulating barriers as part of normal circuit operation. They do this by tunneling, as transistors have been miniaturized over the decades following the trend described by Moore's law, in which the number of transistors on a chip roughly doubles every 2 years. Engineers have had to increasingly account for quantum tunneling in their designs. At today's scales, tunneling is not an exotic phenomenon to be ignored. It is a central engineering concern. The scanning tunneling microscope, invented by Gerd Binnig and Heinrich Rohrer at IBM's Zurich Research Laboratory in the early 1980s, uses tunneling to achieve something almost miraculous. the direct imaging of individual atoms. A needle-sharp metallic tip is brought to within a nanometer of a surface, extremely close but not touching. A small voltage is applied, and electrons tunnel between the tip and the surface, producing a measurable current. This current depends exquisitely on the distance between tip and surface. Even moving the tip by a fraction of a nanometer changes the current significantly. By scanning the tip across the surface and tracking how the current changes, scientists can map the positions of individual atoms with sub-nanometer precision. They can see atoms, they can move them, they can arrange them individually, one at a time. Binnig and Rohrer received the Nobel Prize in Physics in 1986 for this invention. Tunneling also plays a role in chemistry and biology. Enzymes, the molecular machines that catalyze chemical reactions in living cells, often work partly through quantum tunneling, allowing hydrogen atoms to tunnel through energy barriers in ways that make reactions happen faster than they otherwise would. DNA mutations, which arise when hydrogen atoms spontaneously shift position within a DNA base pair, may in some cases involve tunneling. The genetic instructions that have shaped the evolution of every living thing on Earth may bear in their most fundamental moments of change the signature of quantum mechanical probability. Life, in ways we are still unraveling, is a quantum phenomenon. We have travelled an enormous distance together tonight, from the workshops of 19th century physicists grappling with the strange behaviour of heated metal, all the way to the tunneling electrons that flow through the chips inside your phone. Let us take some time now to gather what we have explored, and to hold it all together as one coherent picture. Quantum mechanics began with a crisis. Classical physics, for all its triumphs, could not explain the way heated objects emitted radiation. Max Planck, in 1900, resolved the crisis mathematically by proposing that energy came in discrete packets, quanta, rather than in continuous flows. He was not sure he had discovered a physical truth. Albert Einstein confirmed that he had, by showing in 1905 that light itself was composed of such packets, photons, whose energy was proportional to their frequency. This explained the photoelectric effect, won Einstein the Nobel Prize, and established that quantization was not a mathematical trick, but a feature of reality. From there came wave-particle duality, the discovery that quantum objects, whether photons or electrons or atoms, cannot be classified as simply waves or simply particles. They exhibit both kinds of behavior, depending on how they are measured. The double-slit experiment captures this duality in the starkest possible terms. Unobserved, a particle spreads through space as a wave and interferes with itself. Observed, it collapses to a single definite location. The measurement itself changes the outcome. The wave function, developed mathematically by Schrödinger, Heisenberg, and Dirac, is the quantum mechanical description of a system's state. It encodes all possible measurement outcomes as probabilities. Before measurement, those possibilities coexist. After measurement, the wave function collapses to a single definite result. Heisenberg's uncertainty principle tells us that certain pairs of physical properties cannot both be known with precision simultaneously. Position and momentum are the most famous pair. This is not a limitation of measurement. It is a fundamental feature of wave mathematics applied to the quantum world. One of its consequences is that nothing in the quantum realm can be fully at rest. Zero-point energy ensures that even at absolute zero, quantum particles continue to move. Superposition tells us that quantum systems exist, prior to measurement, in genuine combinations of multiple states. This is not ignorance. It is the actual physical condition of the system. Measurement causes the superposition to resolve into one definite outcome, and the process by which this happens, the measurement problem, remains one of the deepest unresolved questions in physics. Quantum entanglement demonstrates that particles can be correlated across any distance in ways that no classical model can replicate. Bell's theorem, and the experiments that tested it, proved beyond doubt that these correlations are genuine, that the universe is, in a meaningful sense, non-local. Entanglement does not permit faster-than-light communication, but it does enable quantum cryptography, quantum teleportation of information, and may ultimately be connected to the very structure of space-time. Quantum tunneling allows particles to cross barriers that classical physics would declare impassable. It powers the nuclear fusion in the sun, makes modern transistors function, enables atomic-scale microscopy, and touches the chemistry of life itself. Together, these ideas form a picture of the universe that is profoundly different from the one our intuitions suggest. At the deepest level, the universe is not made of definite fixed things moving along predictable paths. It is made of quantum fields and probability waves, of particles that exist in superpositions until they are measured, of correlations that span space without being mediated by any signal, of barriers that are not quite impassable and particles that are never quite still. And yet, and this is the part worth sitting with, this strange counterintuitive framework is extraordinarily successful. Quantum mechanics is, by the standards of experimental precision, the most accurate physical theory in history. Its predictions have been tested in some cases to 10 or more decimal places of precision, and in every test, without exception, the theory has been confirmed. It has never failed. Something that's strange and that accurate deserves our deepest respect. There are still profound things we do not understand. The measurement problem, precisely how and why quantum superpositions collapse into definite classical outcomes, is unresolved. The relationship between quantum mechanics and gravity is one of the greatest open problems in all of physics. General relativity, Einstein's theory of gravity and space-time, describes the universe at large scales with stunning accuracy, but it is a classical theory. It does not speak the language of quantum mechanics. Unifying the two, constructing a genuine theory of quantum gravity, remains an unsolved challenge. Approaches such as string theory and loop quantum gravity are attempts in this direction, but none has yet achieved the status of a confirmed complete theory. Beyond these technical questions lie deeper ones. Why do these particular quantum rules govern nature rather than some other set? Why does Planck's constant have the specific value it does? Is the universe at the level below quantum mechanics even stranger than what we have found so far? Are there deeper layers still? These are questions that future physicists will grapple with. Perhaps some of the people lying awake right now, young minds turning these ideas over and over, feeling that particular quiet electricity that comes from encountering something genuinely new, will be the ones to answer them. Quantum mechanics teaches us, if it teaches us nothing else, that the universe does not owe us intuitive explanations. It does not organize itself for human comfort. At its deepest level, it is stranger than our everyday experience could have prepared us for, and the only way to know it is to follow the mathematics and the experiments wherever they lead, even when they lead somewhere that makes no immediate sense. But it also teaches us that strangeness is not an obstacle. It is an invitation to look more carefully, to think more precisely, to let go of assumptions that were never fundamental truths, just the working approximations of minds evolved to navigate a world much larger and much slower than the quantum domain. The universe you inhabit right now, in this moment, is built from this strangeness. The atoms in your body were forged in stellar interiors, where quantum tunneling made nuclear fusion possible. The electrons in your neurons, moving and firing and creating the experience you call consciousness, are obeying the Schrödinger equation. The photons that carry the light reaching your eyes are moving through space as probability waves, collapsing into definite events only at the moment of interaction. You are not separate from the quantum world. You are made of it. It hums through everything you are. And the fact that we can sit here in the quiet and discuss it, that minds made of quantum matter have developed the tools to examine the quantum foundations of their own existence, that is perhaps the most astonishing thing of all. Let that thought settle gently. Let it carry you into the soft, quiet place where thoughts begin to dissolve and the hum of the universe is the only sound left. The quantum world is always here, strange, precise, beautiful, and inexhaustible. Rest now.